Hello everyone, my name is Trinh Nguyệt Bao. Today we are going to present about chapter 7, uh, process environment. Here will start with our first member, Gia Huang. Let's go.
I'm Nguyễn Quang Gia Hoang. I'm going to present to you about the introduction about this chapter. This chapter focuses on exploring the environment of a single process before delving into process control primitive in the next chapter. Uh, Include how the main function is invoked when the program runs, how command line arguments are passed to a new program, the standard memory layout of a process, how additional memory is allocated, using environment variables, method of process termination, the set jump and long jump functions, and their interaction with the stack, process resource limits. And the next chapter is the main function. A C program begins execution with the main function, where RC is the number of command line arguments, and the RV is an array of pointers to the argument. Before main runs, a special startup function is called, which set of parameters from the kernel, such as arguments and the environment. This startup function is specified in the executable file and is set by the linker during the compilation. The next part is process termination. Um, there are 8 ways for a process to terminate. Normal termination occurs in 5 ways. Return from main, calling acid or acid, return of the last thread from each start routine, calling pthread exit from the last thread. Um, a normal termination occurs in 3 ways: calling abort, receive of a signal, respond of the last thread to a cancellation request. We move to the exit function. Here we have 3 functions. Two first exit function return directly to the kernel, while the third exit performs some cleanup processes before returning to the kernel. Returning a value from the main function is equivalent to calling the exit function with the same value. All 3 functions accept an argument, which is the exit status. If a program ends without providing an exit status, or if the main function does not return a value, the exit status will be undefined. However, if the main function has a return type of in and does not have a return statement, the exit status will default to 0. Uh, the next is add exit function. ISOC allows a process to register at least 32 exit handler functions automatically called by exit function via add-exits. Register functions are called in reverse order of their registration. A program is executed by the kernel through exec functions. A process can voluntarily terminate using exit or exits, or be involuntarily terminate, terminated by a signal. The zip call function can uh, determine the maximum number of exit handlers supported on the platform. The exit functions call exit handler first, then close or open streams. And the four parts in the command line arguments. When a program is executed, the process that performs the exec can pass command line arguments to the new program. This is a standard operation in Unix system shell, as demonstrated in previous examples. And the next, I will show you some demo. The first demo. This will bring Hello World to the screen. Here we have a warning: return type defaults to int because the return type of main is not declared and return value is not defined. So we should use in main and return include instead of assets. So here we have yeah. The second demo about the add assets function. Here we have my asset1 and my asset2. My asset1 and my asset2 are two asset handler functions registered by calling add assets. The program calls add asset my asset2 and register my asset2 once. The program calls add asset my asset1 twice, so my asset1 will be called twice when the program ends. When the program terminates by returning from the main function, the asset handler functions are called in reverse order. Uh, Here, my asset1 is called first time. Since it was registered last, my asset1 is called the second time. Because it was registered twice, my asset2 is called last. So that's the second demo. The third demo is about the argument. Um, Here we have a for loop. The for loop is used to iterate through all the arguments and print them out, displaying in the index and value of each argument. Here we will enter two arguments here. Sorry. Here we will enter two arguments here, and it will print out two arguments here. The zero argument is the name of the program, and that is my presentation. The next part will be by Bảo.
So today I will introduce about the environment list. Each program is also has an environment list, like the argument list. The environment list is an array of character pointers, each pointer containing the address of a new terminated C string. The address of the array of pointers is contained in the global variable environment. The component here, you can see that the environment pointers have the global variable environment. Environment list is contain the array of pointers. Environment strings is individual name equal some value new terminated strings. Convention. By convention, the environment consists of name equal value string. Most predefined names are entirely uppercase, but this is only a convention. There is some exceptions. Accessing the new environment, the environment. access to specific environment variable is normally through the get event and invite get environment or put environment functions. Instead of through the environment variable, but go through the entire environment, the environment pointer must be used. So here is demo. I have here the file in environment list policy. Let's open in test editor to easy to see it. So we have here the global environment variable. This is assessing all environment variable. Here we have the for loop and print the environment, retrieving specific variable by using the get environment shell. Free modifying environment variable. Here we can modifying or put a new environment to environment. So we can so now we print the environment, and then I will run the file here. So gcc -o. I will put a name on it, like the name of the file. So here's the name of the file, policy here, and then run it. This, yeah, here you can see all the environment name here, cell sections or environment variable, and then the specific environment variable that I use the get environment functions to get it, like home and shelf. And then here the line that I modify, and here the new environment that variable that I added, the var hello world. So yeah, next slide. The memory layout of a C program. That segment contains the machine instructions the CPU executes, usually read-only and shareable to prevent the modification and save memory. Example, frequently executed program like text editor, C compiler, and shells. Initialize data segment, often called data segment, contain the variable as explicitly initialized in the program. So we have here the BES segment, that means an initialized data segment, and stand for the block started by symbol segment. It contains variables that are not explicitly initialized to zero by the kernel before the program execution. And then here, stop and heap. Stop will store the automatic variables and information saved during the function call. Each function call create a new start frame, allowing recursive functions to work properly. That contains return addresses, machine register, and space for the automatic variable. Heap used for the dynamic memory allocation. Consistent between the uninitialized data segment and the stack. So here you see the high address and the low address, here the command line argument and environment variables, the stack and the heap. So the stack locate at the high address and grow downward as some more functions are called and local variable allocated. Is the low address is have the heap is between the stack and BES segment here. It's located above the BES segment and grow upward as more memory is allocated. So when the stack pointer met the heap pointer in somewhere between point here, it will free the free memory was exhausted. So so here I have some sample, not so much, but I will use this. I have the size. You can use this to see the size up and like this. Yeah, this is the test segment, the size of the test segment, the size of the data segment, and the size of the assessment. And here is the sum. The the sum of this is a dynamical sum, and this is hexadecimal sum. Okay, share libraries. Share library keep common library routine our executable file. Instead, a single copy of the library routine is maintained in memory, referenced by all the processes. This reduces the size of each executable file but may introduce some runtime overhead when the program is executed or when a shared library function is called for the first time. The advantage here is memory efficiency and easy to update. Used in compilations, different systems will provide options to either use or not use the shared library. For example, the CC and the LD commands can control this behavior during the compilation. I have some demo about this shared library. So let's cd back to the demo file. Home, doc, then demo. So here I have the hello one here. It's just print out the hello world. So now I will use this compile it with the static library hello 1.c. Yeah, we have, and yeah, when you run this, we have the a point out here. So let's bring it at the first time so you can see. Yeah, it's here our hello world. So list the a point out. And here we can see this is the size of the library. But when I use, what happened with I delete this static. So here it will use the share library. We can now we can we doesn't need to print it out, so we can just run this line command, and yeah, as you can see, the memory is optimized than the static one. Memory allocation function, malloc, calloc, and realloc. Memory allocation, the purpose is allocate a specific number of bytes. The contiguous allocation is allocate the space for a specific number of objects, each of a specified size. Realloc is change the size of a previously allocated memory block. It can increase the size, but it may move the memory block to a new location if there are insufficient space. You can decrease the size. It will reduce the size without moving the block, of course. Freeing allocated memory. The purpose here is deallocate the memory previously allocated by malloc, calloc, and realloc. So the consideration here is double freeing. When we freeing the same memory block multiple times, it may lead to a defined behavior. Invalid pointers. Passing pointer not obtained from allocation function to free can corrupt the memory. Pointer alignment. Pointer returned by malloc, calloc, and realloc are suitably aligned for any data. It will ensure that the allocated memory can safely store any data type without alignment issues. So I will have some demo here. The first one is the memory allocation. Here it is the file memory allocations. Yeah, I use the malloc functions, calloc function, and the realloc function that increase the size of malloc function here, and from 10 to 12, from 10 to 20. Okay, and remember to free that pointer, free that memory allocations. Okay, we will run the file here. So here I have run the file the previous time, so I just can run that and don't need to do the compiler thing, the memory demo. So yeah, here you can see the malloc will initial by 1 to 10. The calloc will initial by put the 0 in it, and the realloc pointer, the realloc will increase the size of the malloc from 10 to 12 and put 11 to 20 to the side 20. And about the pointer alignment, when we use the memory allocation function here, we don't have to worry about the this pointer alignment issue. So what is it? Alignment of requirement. I will explain it. Different data types have different alignment requirements. So for example, the short type at 2 byte and must be at an address divisible by 2. The int has an address divisible by 4, and the double is divisible by 8, the address. So why alignment matters? Accessing the misaligned data can be slower because the CPU may need to perform multiple memory access to retrieve the data. In some architectures, misaligned access can cause hardware exception or false. So here you can see that I use the malloc with the in type, double type, and char type without worrying anything. So here I should go to point alignment. Yeah, as you can see, this is the address of three memory allocations that I have just created. So yeah, it don't have any error for now. Memory allocation internals. Implementation typically implemented using the set rate system call to adjust the program data segment, like heap. Heap row generally grow upward. I said before the slide before. Memory pool. When we free the memory blocks are usually kept in a pool for the future allocation rather than being returned to the kernel immediately. Overhead. Allocator may use an additional space for the bookkeeping. I will explain it that when you create a memory allocation like malloc, you will assume that you create it with 1024 bytes. So the allocator here may add an 16 byte more to make it to pointer. It will be a pointer to the other blocks. So that's 16 byte additional space for the bookkeeping. It is overhead. 5. Common memory allocate errors. Here I list to you 3 errors: a buffer overflows, memory leaks, invalid free operations. These errors may lead to the corrupt bookkeeping data, override unrelated memory, assert the available memory, or the program will instability and crashes. So we'll move fast on that. And these two, I just introduced you to the alternative memory allocations, offer a different performance characteristics and features. So here I have the data here about the CPU clock. It will compare. It is a comparison with some the standard, the malloc and gmalloc, port and tcmalloc. So I would like to introduce you the allocate function. The allocate function. The purpose here is allocate memory from the stack frame of the current functions, like some. It's like other memory allocation function. But the characteristic is it will automatic deallocation. Memory is automatically free when the functions return. No free required. Eliminate the need to manually free allocated memory, so we don't have to put the free light. Advantage is simplify memory management for temporary allocations. So it has disadvantage that the stack size limitations and portability issue. So here is the demo. I have here the course of allocate example. Yeah, I use this like not I create the example allocate functions and use the allocate function like as I use the malloc functions. So here the thing here is I was return it. It will free the memory allocation automatically, so I don't need to code the free line here, and when it meets the return, it will free. So let's just run it. Oh no. Yes. So yeah, it's like the previous functions, but it good to use that you don't need to have the manual free step. So that's my presentation. Thank you for your listening. Now is my next member will present it.
My name Khan. I present about environment variable. Environment variable are in the form of name equal value and are used by application, not the unique kernel. The variable can be set in the cell style file. Retrieving environment variable use the GetStanV function to retrieve the value of an environment variable. Some environment variable are defined by the POSIX1 standard. Adding, modifying, and deleting environment variable. Put_env add or modify a variable in the form of name equal value. Set_env set the value allowing an option to override an existing variable. Unset_env remove a variable from the list. Memory management deletion. Easy, simply shift the pointer. Modification may require allocating new memory if the new value is large than the old one. Adding new variable. More complex, add it require memory allocation for both the string and the pointer list. Set jump and long jump function. Set jump and long jump are used to perform a non-local goto, allowing the program to jump back from a deeply nested function to the main function without having to return through its level. How they work? Set jump return 0 when called directly, but return a non-zero value when long jump is called later. Long jump touch an environment variable set by set jump and return value. When long jump is called, it skips the stack frame above and return to the position of set jump in the stack. Variable in long jump. Global and static variable return unchanged after long jump is called. Automatic and register variable have in determine value. Position issue with automatic variable. Automatic variable should not be referenced after the function that declared them had return. And get a limit and set a limit function. Each process had its own resources limit which can be retrieved and modified using the two function. Resource limits are typically inherited from parent processes and are set during some initialization. Limit structure. Limit curve, the current limit. Limit mark the maximum limit. Rule of changing limit. The sublimit can only be changed if the new value does not exceed the high limit. The high limit can be reduced but cannot be increased with the super user privilege. Unlimited limit are specified by a constant limit infinity. Type of resource limit include memory uses, CPU time, core file size, number of open file, stack size, number of child processes, and etc. Some common resource limit value are limit S, are limit CPU, are limit stack, and are limit no file and more. Inheritance of limit resource limit of processes are inherited by its child processes. And program example. The example program demonstrates the difference between global automated static and volatile variable before and after long-term econ. The result vary depending on whether compile optimization are used. Um, and net demo. The code snippet that print out the soft and hard limit for supported resources on the system. And my presentation end here. Thank you for listening.